Computer, okay. Okay, thank you, Kristin, for coming here. I guess you know everyone here very well, so no introductions necessary. So go for it.
Okay, awesome. So yeah, thanks for the invitation. I'll put this in a full screen mode. So it's always fun to get to go back home, and it's even better to do it without jet lag. Also, thanks everybody for meeting me at a non-standard time. I really do appreciate that. Okay, right, so I'm going to talk to you guys about some current ongoing work with Wilhelm Winter on nuclearity and so-called generalized inductive limits. So part one, I want to consider a construction that has really become part of the canon of C-star and operator algebras, and that's the inductive limit construction. So an inductive system, so we start off with an inductive system of C-star algebras. So we just think of this as a sequence of C-star algebras and star homomorphisms connecting the C-star algebras. And from these, so for each element or for each C-star algebra in the sequence, oh, sorry, first let me say, so if we take the sequence of C-star algebras and they take their direct product, so this forms the bounded sequences so the norm bounded sequences of sequences coming from the C-star algebras. And we can take a quotient of that into, or modulo the sequences that converge in norm to 0. So we take a standard quotient map there. And so for each C-star algebra in the sequence, we induce a star homomorphism that takes the kth term, say, into this quotient. By taking for each element A and AK, you just take all of its images along this string inside of the inductive system. And then this forms a bounded sequence, and you just look at where that got sent in the quotient. So this is basically the general proof, more or less, that one can always construct an inductive limit of an inductive sequence of C-star algebras. And in order to get the limit, you take the union of all of these images and take the closure inside of this C-star algebra that's this quotient space here. So this inductive limit construction is, like I said, has really become canon in C-star algebras. And first of all, for providing many interesting examples of C-star algebras. So one very well-known class of examples are the approximately finite or AS C-star algebras. These are inductive limits of finite dimensional C-star algebras. A favorite one for this is the Car algebra, where the finite dimensional C-star algebras are the 2n by 2n matrices, 2 to the n. Another class are these approximately circle or AT algebras. And so these are inductive limits where the C-star algebras in your system are direct sums of matrices over continuous functions on the circle. And a very important class of examples and a non-trivial proof to say that this belongs to this class of examples are the irrational rotation algebras. And so these are the C-star algebras that completely capture the topological dynamical system that you get from an irrational action of the integers on the unit circle. And so another class of examples are also, in a sense, generalizing these. These are approximately homogeneous or AH algebras. And these are inductive limits of homogeneous C-star algebras. And equivalently, we can say that homogeneous C-star algebras look like matrices, some sort of matrix amplifications of continuous functions on some finite CW complex compressed down by a projection. And it turns out that these actually capture a lot of really interesting classes of C-star algebras, in particular cross products, which are a C-star generalization of dynamical systems. But really part of the motivation for studying inductive limits comes from their importance in the von Neumann setting, where the construction is the same as we did before, except for one will take a strong closure instead of the norm closures that we took. Throwing in a definition here. So von Neumann algebra is said to be injective So we think of a von Neumann algebra as sitting inside of bounded operators on a Hilbert space. It's injective if there exists a conditional expectation from the bounded operators on the Hilbert space onto the von Neumann algebra. So this is just a contractive linear map that's the identity on the von Neumann algebra. And why am I bringing that up? Because Kohn, in really the work that eventually won him the Fields Medal, proved that any injective von Neumann algebra is an inductive limit of finite dimensional von Neumann algebras, which we use the word hyperfinite for. So these already have created, because of Kohn's work, hyperfinite von Neumann algebras have become really a central part of the study of von Neumann algebras. Well, they already were, but even with more robust theorems underlying it. And one particular outcome is the classification of Kohn and Hagerup of injective von Neumann factors. So in light of its role for von Neumann algebras, the inductive limit construction has been used to shed light on the structure of many naturally occurring C-star algebras, like the guys we saw before. And we get corresponding C-star classification results, for instance. So the C-star version of the Kohn-Hagerup classification program is the Elliott classification program. And a C-star algebra fits into this classification program if it can be distinguished from other C-star algebras in this program by just considering its K-theory, which is an operator algebraic K-theory, and its space of traces. So really what we first thought was the C-star analog of Kohn's work was Elliott's classification of these AF algebras, these algebras that arise as inductive limits of finite dimensional C-star algebras. But then it turns out what really kickstarted the program was that Elliott realized that, moreover, actually AT algebras plus some assumptions, these can also be classified. And this kickstarted this huge Elliott classification program that was really recently resolved about 5 or 6 years ago, and is actually still getting a lot of active research even today. And also, since I pulled up the example anyway, these AH algebras, also with some extra structural assumptions, these can also be classified. So we have a lot of interest in C-star algebras for looking at inductive limits. But the more that one actually works with these inductive systems, the more one realizes that on-the-nose behavior at each step is superfluous. And the mantra that one should take is that asymptotic behavior is really what matters. Following this philosophy, Blackadar and Kirchberg introduced the generalized inductive systems of C-star algebras. And this is where those connecting maps, which before were star homomorphisms, only asymptotically behave like star homomorphisms. And they show that the limits of such systems actually form an important class of C-star algebras. So they actually really systematically go through and relax every single property of a star homomorphism: linearity, star preserving, well, actually additivity and scalar multiplication, star preserving, multiplicative. And I'm not going to actually go into that full generality. I really want to focus on a special class of systems that they looked at called NF systems. So an NF system is a sequence of finite dimensional C-star algebras together with asymptotically multiplicative, completely positive contractive maps connecting them. So let's dissect what I just said. So first of all, completely positive contractive maps. So instead of assuming that these maps between the C-star algebras are star homomorphisms, we instead look to a more readily available class of maps. And these are completely positive maps between C-star algebras. So positive means that they send positive elements to positive elements. Completely positive means this stays true under matrix amplification, and contractive just means norm decreasing. But these are actually much more readily available than star homomorphisms, but they still can retain a lot of the structural property of the C-star algebra. So what does the asymptotically multiplicative mean? So asymptotically multiplicative means this super technical definition, and this is the only time I'm going to expose you guys to one of these asymptotically blank definitions in the talk, but it's good to look under the hood at least once. So what this says is that if I take any fk in the sequence, any C-star algebra in the sequence, and I take two elements in fk and some tolerance epsilon, then if I go far enough down along the sequence and I look at the image of x in the nth term in the sequence, and the image of y in the nth term, if I multiply them there, then that gets, and then apply the next round of maps, then that's really, really close to multiplying rho mk of x with rho mk of y. So this is supposed to try to give you a good idea, or this is supposed to try to get close to multiplicativity. Multiplicativity would tell you that rho mk of xy is equal to rho mk of x times rho mk of y. I should remark that this is more complicated than the naive approach. So the naive approach would be to say, okay, I want, instead of this complicated expression, to look at rho mk of xy minus rho mk of x times rho mk of y. But this actually really does place too much importance on something that's just happening in the kth C-star algebra, at the kth step, and it introduces too much of an error and it's too restrictive. So we actually do end up with pretty technical looking statements like this. So the limit of an NF system is formed just like we did before. We take induced maps from the finite dimensional C-star algebras into the quotient algebra and take the union, take the closure. And it turns out that this guy still actually is a C-star algebra, because the quotient only really cares about what happens asymptotically. So the asymptotic multiplicativity actually gives us multiplication in the limit. And the limit we call an NF C-star algebra. So why do we care about NF C-star algebras? Well, here's one reason. So Blackadar and Kirchberg showed that if you take a separable C-star algebra, it is NF, meaning it's isomorphic to one of these generalized inductive limits, if and only if it admits a CPC approximation with asymptotically multiplicative maps. So what do I mean by that? There exists a sequence of finite dimensional C-star algebras, Fn, not assuming that it's coming from that sequence that we saw before. In fact, that's a little bit too nice to work. But still, sequence of finite dimensional C-star algebras and completely positive contractive maps going from A into the finite dimensional C-star algebras and back, so that their composition converges pointwise in norm to the identity on A, and so that these maps psi going from A, going out of A, they get closer and closer and closer to behaving multiplicative, behaving like homomorphisms. Okay. So in particular, these C-star algebras are nuclear, because if I gray out this asymptotic multiplicativity, I've basically given you the definition of nuclearity through the completely positive approximation property. Many times, if you've seen the completely positive approximation property, you see it in terms of this approximately commutative diagram. So this is exactly the same expression up here as this composition converging pointwise in norm to the identity. A lot of times we like to draw it in a pretty diagram. You will see that pretty diagram again. Okay. So what Blackadar and Kirchberg also show is that these NF C-star algebras are exactly the separable nuclear C-star algebras, which are also quasi-diagonal. And what does quasi-diagonal mean? So a separable C-star algebra is quasi-diagonal if it admits what I like to call a separating family of finite dimensional almost representations. So that means we have a sequence of CPC maps going from A into finite dimensional C-star algebras, which are pretty close to being actual representations. So they get closer and closer to being multiplicative, and they're separating. So that means that they get closer and closer and closer to actually realizing the norm of any element in A. So they were able to completely classify separable nuclear C-star algebras, which were quasi-diagonal. And that was really the strongest thing that we could come to in terms of Kahn's injective implies hyperfinite. So I'll get to that a little bit more later on. But the question right now is, can we tease out this quasi-diagonality? Well, the problem is, if we want to tease out quasi-diagonality, it was really, we caught it by imposing this asymptotic multiplicativity assumption. But the problem is, if we try to relax this asymptotic multiplicativity assumption, then the inductive limit is going to fail to be an algebra. That's the whole reason that that assumption was put in place, was to guarantee that the actual limit is a C-star algebra. So the question is, how can we capture nuclear C-star algebras and somehow or other separate it from this quasi-diagonality, but still actually get a C-star algebra? So we need to relax multiplicativity without losing C-star structure and enter order 0 maps. Okay, so what is an order 0 map? So if we take a completely positive map between C-star algebras, it's called order 0 if it's orthogonality preserving. So that means that if I take two positive elements whose product is 0, so they're orthogonal, then the product of their images is also 0. So you can also talk about orthogonality for generic elements, not just positive elements, but because of the importance of positive elements in a C-star algebra, it suffices to define this for positive elements. So what are some good examples? So if you take the characters or the multiplicative linear functionals on a C-star algebra and weight these by positive scalar values, these will always give you a order 0 map. If we took so if we take a multiplier, so going to be a linear functional going from continuous complex valued functions on the interval 0, 1 to itself, and we just go by multiplying functions by some positive real valued function, then this will also give us a CP order 0 map. How do I know? Because more generally, if we have a star homomorphism between two C-star algebras, and I take some positive element in the domain space that commutes with the image of the star homomorphism, then the map where I take the star homomorphism and then just multiply what it spits out by this positive element, that's CP order 0. And it's actually pretty easy to verify that that's CP order 0, because basically since this positive element commutes with pi, it just gets out of the way of this orthogonality. But what's really remarkable is that Winter and Zacharias show that that's actually basically the only way that you can get a CP order 0 map. So this is an oversimplification of the structure theorem, although what I'm saying is still true, is that every CP order 0 map can be written as the compression of some star homomorphism by a positive element that commutes with the image of the star homomorphism. I tweaked the way I wrote this a little bit because I want to juxtapose this with another bad retelling of Steinspring's dilation theorem. So oversimplifying Steinspring's dilation theorem, you can say that every CP map, so take off order 0, can be written as the compression of some star homomorphism by a positive element in the image. So really the key difference here is this extra commutivity. And it turns out that that is going to be extremely powerful. Okay, so an upshot from Winter and Zacharias' theorem is that if I've got two C-star algebras and I have the domain C-star algebra unital, then a CP map between the C-star algebras is order 0, if and only if it's almost multiplicative, except I have to pay the penalty of multiplying by the image of the unit. Now, notice what this says is that if I have a CP order 0 map that is actually unit preserving, it's automatically a star homomorphism. So I am probably assuming, unless some of my, okay, so my statements will get trivialized otherwise, but by and large, we're assuming that these maps are not unital. So structurally, these sit between CP maps and star homomorphisms, and they actually will retain a lot of nice properties of star homomorphisms that aren't always a given for CP maps. So one of them we've already sort of implicitly seen. Oh, I forgot an F. It's Wolf with 2 Fs. So Wolf proved before Winter and Zacharias that if we have a CP order 0 map from a unital C-star algebra, then the unit commutes with the image. Definitely not always true for just a regular CP map. So a consequence of Winter and Zacharias' structure theorem is that if you have a CP order 0 map between C-star algebras, then it turns out all of the matrix amplifications are automatically going to be CP order 0. So in other words, an order 0 map is already completely order 0. Here's another fun thing. So if the CP order 0 map happened to be injective, then not only does it send positive elements to positive elements, but if any element in A gets mapped to a positive element in B, then I already know that it was positive in A. So combine that with the previous proposition, and we can say that if a CP order 0 map is invertible on its image, then its inverse is automatically completely positive. So this can be seen as a bit of abusive notation, but it turns out that actually, so completely positive maps, you usually assume that you're defining it on some sort of operator system. It turns out that there is an abstract operator system floating around that's keeping me from lying, which is basically just the image of A and the positive structure it inherits from B along with the image of the unit. So now on to the images of CP order 0 maps, which is where our current research starts to kick in. So it turns out that a CP order 0 map really leaves an impression of its structure in the image. And I mean it when I say that it's the structure of the CP order 0 map and not just the C-star algebra. So this is even to the point that we can detect when a self-adjoint subspace of a C-star algebra is the image of some CP order 0 map, but I'll get to that a little bit more later on. Actually, the starting point is that this preserved structure is enough to allow us to build a C-star algebra outright out of the image. So I need to actually highlight which structure I'm talking about because these maps are really rife with structure. So if I take a CPC, so now I'm going to just restrict to the contractive setting because it'll make my life easier. So if I take a CPC order 0 map from a unital C-star algebra into some other C-star algebra, I'm going to write X for the image of the C-star algebra and E for the image of the unit. And what we get is the following. So Wolff's theorem tells us that E commutes with X. Rephrasing Winter and Zacharias' theorem, we can say that the sets X squared is equal to EX. So you can think of this as for A and B and A, psi of A times psi of B is equal to psi of 1 times psi of AB. So this was multiplicative modulo multiplying by an image of the unit. And finally, E is an order unit for X inside of B. So this last bit I need to define. So we say that a positive element E in a self-adjoint subspace of a C-star algebra is an order unit if, given any self-adjoint element in X, there exists a positive scalar R. So if I scale up E by R, then it will dominate X in the sense that the difference is positive in B. So the obvious example here is just the unit of a unital C-star algebra. This is an order unit, right? And in this case, R is just going to be the norm of X. More generally, though, we can have these in a non-unital setting, right? So we take the continuous functions on the half-open interval that vanish at 0 and take just the canonical image of the complex numbers embedded inside of the C-star algebra. So these are going to be the scalar multiples of the identity map. And the identity map is going to be an order unit for this subspace. And actually, more generally, if you just take a CP map between C-star algebras, then the image of the unit is going to be an order unit for the image of the C-star algebra. And again, if you've seen the term order unit before, I definitely borrowed that from sort of this Choi-Efros construction of abstract operator systems. And I'm not lying when I borrow that language. There is actually, if you are looking for one, there is an operator system floating around. And this E is the order unit for that operator system. So in particular, the operator system consists of my subspace X, the positive structure it inherits from the C-star algebra B, and this order unit E. Okay, so let's see. This is blocking my slide, so I can't see it so well, but right. So we're actually taking an extra assumption, which is that E commutes with X. Now, once E commutes with X, so E is a positive element and it's commuting with X. And so that means that now we actually really get to access the functional calculus of the ambient C-star algebra B. And we can conclude a lot of information about X by moving outside of X. So here's one sample of the sort of thing that we can get. So if we have a self-adjoint subspace of a C-star algebra that commutes, that has an order unit that commutes with X, then first of all, it has this nice separation property. It actually satisfies much stronger separation properties than this, but two elements are equal if and only if their products are equal, or their products times this order unit are equal. So these products don't land in X, but they can still tell us something that happens inside of X. And likewise, E can completely detect positivity inside of X as well. Okay, so back to those three highlighted properties of the image of a CPC order zero map. And it turns out that these are actually enough to define a pre-C-star structure on a self-adjoint subspace of a C-star algebra. So what do I mean? Let's take a C-star algebra B and a self-adjoint subspace X and a positive contraction E and B that satisfies those three criteria we saw before. E commutes with X, X squared is equal to EX, and E is an order unit for X. Then we can define an associative bilinear map on X, which actually satisfies the following. So this equation that it satisfies is sort of like it's technically very powerful, but the main upshot is that X along with this new bilinear map forms a star algebra with E as its unit. What this expression right here is telling you is, moreover, there's a very intimate sense in which this new multiplication that I'm acting on X plays well with the multiplication that's happening on B. So here XY, this multiplication is in B, is equal to E times this element X bullet Y. This lands in X, and this multiplication here is also in X. So moreover, there actually exists a pre-C-star norm, X bullet, on this new star algebra. And so that means that with respect to this new associative bilinear map, this new multiplication that I've defined, this norm satisfies the C-star identity. And so when I close it off with respect to this norm, I get a C-star algebra. So what that means is if I've got a self-adjoint subspace of a C-star algebra B with distinguished positive element that satisfy those criteria we saw in the previous theorem, we get a pre-C-star structure on that self-adjoint subspace. So since these three criteria take up a big chunk of space, I'm going to call them together C-star. So when X and E satisfy C-star, we can define multiplication on X and a pre-C-star norm on X with respect to that multiplication. So I'll write C-star of X, or C-star bullet X, as the completion. So this is the C-star algebra that comes from viewing X with this different multiplication. So what is this C-star algebra? Well, it turns out because of this special interplay with this bullet multiplication and the multiplication on B, it turns out that if E were actually the unit of B, then X would be a star subalgebra of B, and C-star of X would just be its closure. So not so exciting. But it turns out if X is already closed in this bullet norm, so if this completion doesn't add any new elements to X, then the C-star algebra, the C-star bullet X, can be identified with the enveloping C-star algebra for the abstract operator system that I flashed before. So this enveloping C-star algebra is basically just a minimal universal structure, or minimal universal C-star algebra that can be attached to a given operator system. And it turns out that our construction does recover it for this particular operator system here. Oops. Not enough pauses there. So X is actually closed in this bullet norm, for instance, when X is already closed in B, or when X is the image of a CPC order zero map. And another instance where we can tell you really concretely what this C-star bullet of X is if X and E was already the image of an injective CPC order zero map. So if we have a CPC order zero map from a unital C-star algebra, then the composition of psi with the identity map, so we just take, so X is just a subspace of B, and because X is the image of a CPC order zero map, which means that its closure with respect to the bullet norm, which is the C-star algebra here, it means X and C-star bullet X are equal as sets. So the identity map just basically re-identifies X. And then when I compose this identity map with psi, I get a star isomorphism between A and C-star bullet that basically just factors through X inside of B. And then that also happens to be the same thing as the enveloping C-star algebra. Okay, so let's see, how am I doing on time? I think I can quickly say what's on these guys. Okay, so more generally, we can actually talk about we can recover our initial motivation, which was the images of CPC order zero maps, because—
Kristin, let me just ask on that previous slide, maybe you're about to say it, but if you have one of these C-star satisfying subspaces in E, can you realize it or as it means that you can build an injective CPC order zero map from C-star bullet onto X, something like that, or you know, like converse of this construction. Is that are these all of them? Maybe you're going to say that, but I can't. I just go ahead.
Yep, that's exactly what's coming up. And the answer is provided X is closed. But in general, yeah, so in general, if we just have a, right, so in general, if we have a self-adjoint subspace with a distinguished positive element where the pair satisfies C-star, then if you take the identity map that identifies X as a dense subspace of this C-star algebra with X as a subspace of this C-star algebra, this extends to a CPC order zero map between the C-star algebras. And all of this together really gives us the following characterization for a self-adjoint subspace with distinguished positive element is that if you satisfy these C-star criteria and you were closed with respect to this bullet norm, in other words, the C-star completion doesn't add anything, then this is equivalent to saying that you are the image of a CPC order zero map where the unit actually got sent to E. I mentioned this before, but the image of a CPC order zero map will automatically be closed in this bullet norm. So this is something extra I have to add on. But it turns out that if I'm working in a closed self-adjoint subspace, then I get a little bit more, because if it's closed, then X is automatically closed in this bullet norm. So I get to drop that pesky criterion and say that the pair X and E satisfy C-star if and only if there is some unital C-star algebra, which is secretly this bullet C-star algebra, and an injective CPC order zero map from A into B where X is the image. So in particular, what David was asking is that, yeah, this identity map becomes a CPC order zero map. It's injective in this setting, and also X is closed. And so I've got a injective bounded linear map with closed image, so it's actually going to be invertible. And once you have an invertible order 0 map, remember that it actually ends up being, its inverse will automatically be completely positive. So now I've got a complete order isomorphism. And just a quick fun note here is that we can actually do a little bit more. We can even, by closely examining what happens to the image of the unit, we can tell whether the image of a CPC order 0 map was closed. And that's basically going to come down to the image of the unit not just being a unit, but actually being a unit in a very uniform way, sort of with respect to the norms of the elements in X. But I don't want to delay this too much because I want to actually get onto the upshot results instead of the fun technical stuff in between. Okay, so back to these NF systems that I started with. So remember that the whole reason I went into these order 0 maps was that I want to relax this asymptotic multiplicativity requirement from these NF systems of Blackadar and Kirchberg. So here was the definition again. So sequence of finite dimensional C-star algebras with connecting maps that are not quite star homomorphisms, but asymptotically they act like star homomorphisms. And the issue, and we wanted to relax asymptotic multiplicativity because these systems sort of automatically pick up quasidiagonality, and we don't want them to automatically pick up quasidiagonality. But the problem is if we drop multiplicativity or asymptotic multiplicativity, then we lose C-star structure. But now we're equipped to overcome the hurdle. Okay, so generalizing the generalized inductive limits. So now I want to consider a sequence of finite dimensional C-star algebras with CPC connecting maps. So I've dropped asymptotic multiplicativity, just CPC connecting maps. Then we can still, just like we did with inductive limits all along, we have induced CPC maps into the quotient algebra, which I'm going to start calling F infinity because it fits on the slide. And we can still form the inductive limit by just taking the union of all these algebras and closing it off. And that's no longer going to be a C-star algebra, but it's going to be a closed self-adjoint subspace of the C-star algebra, which I've been talking about for the past 20 minutes. Right, so again, though X might not be a C-star algebra, if we can guarantee that there is some positive contraction in this F infinity so that X with this E satisfies C-star, then it will be completely order isomorphic to the C-star algebra, C-star X bullet, via that injective CPC order 0 map. So the task now is to encode C-star into a system, into this system of CPC maps between finite dimensional C-star algebras. So now I need to unpack C-star because I want to actually encode it. So remember that C-star were 3 criteria. Well, secretly 4 criteria, because I wanted E to be a positive contraction. I want it to land in X. I want it to commute with X. I want it to satisfy X squared is equal to EX, and I want E to be an order unit for X. So I want to encode these things into the sequence. So first thing I want to encode is finding a positive contraction that lands in X and commutes with X. So I'm going to spare you guys of the technical definitions. I told you I would only subject you to it once with asymptotic multiplicativity. So I'll just give you a feeling for what we try to encode. So to come up with the sequence E, we come up with a bounded sequence in F1 that is what we call asymptotically coherent, which basically means that if I look at the images of each of these ENs, when they land inside of the quotient space, F infinity, or the quotient of the product mod sum. So all of these maps all of these guys are going to land in X, and I want to sort of choose my sequence EN so that these will actually form a Cauchy sequence in X. Since X is closed, that means that their limit will be in X. So I also wanted to choose it to be asymptotically central, which guarantees that the limit of that Cauchy sequence will commute with X. Okay, so that's what I'm going to do to get E in X and E to commute with X. to ensure that E is an order unit for X, we require that the sequence is what we call an asymptotic uniform order unit, which, just short to say, we encode the order unit into the sequence. So under all of these assumptions, we get a positive contraction that commutes with X and is an order unit for X. So we'll call the sequence an asymptotically central order unit. So I think I'm going to jump through this slide for the sake of time, but suffice to say, we can also encode this notion of x squared is equal to EX. So we can actually encode all of this information into our system. And by encoding all of this information into our system, we get a generalized NF system. So a generalized NF system consists of a sequence of finite dimensional C-star algebras with CPC connecting maps like we had before. And I want these CPC connecting maps to be what I would call asymptotically order zero with respect to this asymptotically central order unit. And this asymptotically order zero is this criteria that I just skipped over that got you that x squared is equal to EX criteria. But basically, you should think that this is the order zero relaxation of star homomorphism. So this is the asymptotic version of relaxing star homomorphism to order zero. Okay, so what's an example of an generalized NF system? Well, it turns out combining, really having a hard time citing where this really originally appeared in the literature. But looking at work of Blackadar and Kirchberg, Winter and Zacharias, Brown, Carrion, and White, and then along with me and Wilhelm, you can say that any separable unital nuclear C-star algebra admits a CPC approximation, so that if you take those finite dimensional C-star algebras, and then you take, basically you just follow that zigzag that I showed you before. So you start in Fn, then you go back up to A, then go into Fn plus 1, then go back up to A, and so forth. Take this composition. These form your intermediate maps. And then the images of A under these, or images of the unit of A under these downwards maps, these will actually form a generalized NF system. So let's actually see how that works. So if you take a CPC approximation of the unital C-star algebra, with, so this is where we needed Blackadar, Kirchberg, Winter, Zacharias, and Brown, Carrion, and White, is that you can always choose a CPC approximation where these, what I call downwards maps, the maps from A into the finite dimensional C-star algebras, are asymptotically order zero. So this is the same, this is the order zero version of the asymptotic multiplicativity that I used to define quasidiagonality before. And it basically just is this asymptotically multiplicative modulo multiplying by the image of the unit. So if we take such a CPC approximation as we know we're guaranteed to have, what this will do is the downwards maps, these psi ends, are going to induce in the limit a CPC order zero map from A into the sequence algebra, which is the direct product among the direct sums. It turns out that after passing to a subsequence, we can actually arrange it so that psi hits what ends up being the limit of these finite dimensional C-star algebras here too. So it does take some fiddling to actually make sure that psi hits the limit, but you can always arrange for this to happen. And then psi is going to be a CPC order zero map that gives you really a complete order isomorphism between X and A. And the fact that psi is CPC order zero will basically mean that X as the inductive limit of this system, I should say, so X being the image of an order zero map means that X along with the image of the unit will automatically satisfy C star, and then we can sort of back encode that into the system. And so then our system will actually be a generalized NF system. Right. Okay. So the reason we introduced C star was so that we could drop asymptotic multiplicativity and keep the C star structure. So by encoding C star into our definition, we've guaranteed that the inductive limit along with this induced order unit satisfies C star. And so what we can say is that the inductive limit of a generalized NF system is completely order isomorphic to a unital C star algebra, in particular C star X bullet, via an injective CPC order zero map. Okay. All right. Moreover, if A is a unital C star algebra, and I had some injective CPC order zero map, implicitly I'll call it psi, going into F infinity, and its image was X, then from a theorem that I threw up in the images of order zero map section, that means that A is actually going to be isomorphic to C star bullet X, which means that in that example we had before, when X arose as a generalized inductive limit, or the generalized NF system arose from a CPC approximation of a unital nuclear C star algebra, then this X, the C star structure that I could build on this limit, actually recovered that nuclear C star algebra. So in other words, what we have is, at the end of the day, at the end of this picture here, I had this one-to-one correspondence between A and this inductive limit X, and now I've got a isomorphism between A and this C star algebra here that I was able to induce on X because X satisfies the C star criterion. But now the bigger question is, okay, so this is definitely a class of C star algebras arising as limits of generalized NF systems that are nuclear, but given any generalized NF system, will the associated C star algebra be nuclear? Have we actually dropped quasidiagonality from Blackadar and Kirchberg's results? Okay, so how could we actually prove that? What do we have? What we have are the sequence of finite dimensional C star algebras and induced maps into their limit, which is this X. Now, because X is guaranteed to satisfy the C star criteria, I have an injective CPC order zero map corresponding between X and this C star X bullet. It turns out from some of these things that I showed to you before about these order zero maps, the inverse of this map is also going to be completely positive. And so that means if I compose these rows with the inverse of the identity maps, then I get CPC maps directly from finite dimensional C star algebras into the C star algebra. So let's drop the middleman. And what I have is now starting to look an awful lot like a completely positive approximation. So the question is, can we come up with downwards maps to get a completely positive approximation? And this is actually an open question right now that Wilhelm has been pretty heavily publicizing. It turns out that in some cases, if one works really hard and digs in the literature, then yes, if we assume that the upwards maps are, these are decomposable into a direct sum of a bounded number of CPC order zero maps, which is a lot to digest right now, enough to say, suffice to say that this is basically encoding finite nuclear dimension, if you've heard this word. But it turns out we don't actually need that. We can get around it because of our construction actually fits perfectly into Ozawa and Sato's one-way CPAP. So I'll go ahead and give the statement of the theorem, but I don't have time to say why we fit into this structure or really exactly what the theorem says, but it suffice to say they give a one-way version of the CPAP in terms of a C star algebra is nuclear if and only if there exists a net, or in our case, a sequence of maps, these upwards maps coming from finite dimensional C star algebras into our C star algebra A that satisfy some nice criteria. And it turns out ours fit into this like lock and key. I do want to remark that this really is sort of a more formal argument. So their proof goes by showing that the double dual of A is hyperfinite. So the question of can you always construct these downwards maps is still open. But suffice to say that that's enough for us to continue on. And we can actually now say that the inductive limit of a generalized NF system is now completely order isomorphic to a unital nuclear C-star algebra via an injective CP order 0 map. And now to tie it back up with what we saw before, remember that Blackadar and Kirchberg's characterization of NF algebras, as these were exactly the algebras that were both nuclear and quasi-diagonal. So nuclear and quasi-diagonal means that you're star isomorphic to an NF algebra. And this asymptotic order 0 has allowed us to replace asymptotic multiplicativity with asymptotic order 0. Has been able to let us replace or just drop the word quasi-diagonal. Right, so what we can say then is that a separable C-star algebra is nuclear if and only if it can be realized as the limit of a generalized NF system. So we don't get to say something like a star homomorphism because the limit of the system might not be a star algebra, but this injective CPC order 0 map is really the one-to-one correspondence that one can get in this sort of situation. And so this is the statement of the theorem again. And just to put it in a little bit of perspective, we like to think of nuclearity as sort of the C-star analog of injectivity. And so this is why we can say that this is the C-star analog to Kahn's theorem for Inductive von Neumann Algebras. So this is exactly characterizing the nuclear C-star algebras as generalized inductive limits in the right setting. And that's all I had. So thanks.
Thank you. Thanks for the nice talk. Do you have any questions for Kristin? Joe is emphatically clapping in the text, by the way, in the chat.
Mm-hmm. So are there, I mean, I guess it's probably too early for this, but do you know if there are other applications of this theory? Like, it seems similar to what I've heard about things like E theory and things like that. Do you think there are applications to other sort of K theory type questions or?
Oh yeah, definitely. We're actually, the next step is, so we've already been able to construct K theory for these operator systems. So one can actually just use basically the implicit multiplicative structure there and build K theory from the ground up. And you can actually show that it's K theory, it's going to correspond in an incredibly robust way with the K theory on this C-star bullet. So we've actually already been able to build the K0 and K1 groups. And then the next step is going to be encode this into the finite dimensional systems. And then fingers crossed, come up with some finite dimensional version of the Kunev theorem, which is a sort of proof of concept for the UCT.
Thanks.
Any other questions?
Ben's already seen this talk like 4 times, I think.
Yeah, but I somehow didn't think about this question the first 3 times. So
that's cool. You're a trooper. You sat through it 4 times.
Yeah. 4th time's a charm. I think that's what they say.
Maybe I'll just ask that same question again, since I didn't really understand the answer. How can you recover the K theory of A out of the sequence? I mean, or to what extent can you, or what's going on when you try to do that?
So the step of recovering the K theory from the sequence, that's the next thing to do. So that's not something that I've actually really sat down. And so I don't want to say anything be poorly misguided. because you can, of course, have issues of even in just looking at inductive limits of C-star algebras, where a wealth of projections really only arise in the limiting structure and nowhere in the finite dimensional approximations. So this is like a non-trivial challenge to try to pass it to the sequences. So that's more of like the next goal.
So if there are no other questions, thank you again. Let me stop recording. And
I guess what I meant is really